Ja, de pen erbij pakken. Goed, dus werkt dat dan ook. Yes. Oké, dat werkt ook. Checken. Ja, het is helemaal al live. Niks aan de hand. Geluid uitzetten. Nee, dat klopt ook niet. Live. Jo, geluid is uit. Dat is goed. Okay, students, welcome back to the second half of the Multibody Dynamics course. Again, it's a bit a strange situation. I'm sitting here at home talking to my camera and to a screen. On the screen I have projected a number of students, which might help to get me a little bit more focused. I will show you in a second. So this is my other screen, and you see some students sitting there. Hopefully that will keep me a little bit more focused in this lecture, because it's really hard to have no audience. Okay, today's topic, lecture 7, closed loop systems and coordinate projection method. It's chapter 16 in the book. I think all systems are running, live stream, everything, so looks good. And of course we start with Kahoot, right? So let me see where the quiz is. Yeah, and it's in-class quiz number 7, which means it's about most of the material is from the past, right, from the previous, and a little bit from the today's lecture. Okay. Play, right? No, I've done something wrong. Forget it. I have to do this. Yeah, classic. Audio is not interesting. Yeah. No, I'm not going to do that. Okay, stay with this. I will just have to wait for the number of participants to sign in. According to the live stream on YouTube, we have 108 people watching. So around that number should also be present in the quiz. Of course, a little bit more, because people can share up, right, to sit with multiple people behind one computer. Okay. Looks pretty stable, so let's start the quiz. Okay, first question. Which numerical integration scheme was used? So here you see this plot, this convergence plot about using different step sizes for the error estimation. And we have different schemes, of course, with different order, and from the plot you can guess what the order was, and then you can guess what the scheme used was. And in class I always say, please discuss among each other. I don't know if you're sitting in groups, then please discuss. Unfortunately, that's a thing which we now miss out on. Yeah, there's about a 10-second delay. So for those in the live stream, it's 5, 4, 3, 2, 1. Yeah. And then I'll just have to wait until my count goes down to 0. Okay, everybody answered. Yeah, it's an RK3 scheme, and it's easily shown. If you look at the slope and you guess, then on one horizontal one you see 3 vertical ones, so meaning that the global arrow is order 3. So we have an RK3 scheme. Very good. Hoin. I don't know why people said Hoin. Okay, second question. Stability region for such a RK3 system is, and we see a number of stability regions. Stability region meaning that if your eigenvalues of the system are within this region, h lambda, then it should be stable. This is not too hard, actually. You can just look it up. Okay, everybody should be there now. Okay. Yeah, the correct answer was of course B. Very good. Let's get to the next one. This is about different integration schemes. Again, we use a RK3 scheme, and here's a way of writing down the RK scheme. And then the question is, how do you determine then the final value? And there are 4 possibilities of using these 3 intermediate slopes. Okay, this is a little bit more difficult, it turns out. Some of you go for the green option, for this one below, but the majority goes for the correct answer. Well, you can rule out already a number of things. Suppose you have constant acceleration, then you add up 3 accelerations here, then it should be h divided by 3, otherwise it doesn't work, right? And likewise here, and here likewise. So actually, without looking it up in the book, you can already come to the conclusion that it must be the right thing, because 2 plus 3 plus 4 equals 9, and here it doesn't add up. Okay, next question. This is about estimating the error in the solution. Take your time, the calculation is not so hard. Okay, looking at the answers and the time left, we see that this is really a hard question. Yeah, this is really a hard question. Okay, so let me exemplify a little bit on this. So the majority is wrong, right? It looks like a lot of people have been guessing, because we have this distribution. Okay, well, let me erase the question again. Put show the media, right? So we find two solutions with step size h and h over 2. Then what we do, we take the difference of these two solutions, which is 0.0007, right? So 3 zeros and a 7. But as you know, there's a constant in front of the error estimation, and it has to do with the power. So it's 1 over 2 to the power p minus 1. And since p is 3 for the RK3, you get 2 to the power 3 is 8, minus 1 is 7. So it's 1 over 7 times 0.007. So it should be 0.001, which is the error estimate. And then, of course, the error estimate is on the most accurate solution. So looking at the answer, we see here, well, the first two answers are with a less accurate step, with a larger step size. So those two already go away. So then we are stuck with these two. So the most accurate answer. And then, as an error, we have not 0.007, but 0.001. So therefore, green is the correct answer. Okay, next question. That is the last one. That's about the topic of today. So we have an undetermined set of equations. So we have more variables than we have equations. So we have an infinite number of solutions. And then I want to find a solution which minimizes sort of the vector x, so it makes it shortest to the origin O. So I gave 4 solutions, and then the question is which is the correct solution, or which is the one which has the shortest distance to the origin. Yeah. Okay, most of you have the correct answer, so there's little, I can exemplify a little bit. There are, of course, a number of infinite solutions, and if you check like the first and the second, they fulfill the equation. The third doesn't even fulfill the equation, so that drops out. But then if this distance to the origin is 1, this is a square root 2, and this is even less than 1. Okay, so that finishes the quiz with on the podium student IDs. I have no clue who they are. Prasad, second, and number first is... Okay, congratulations. I don't know who that is. Please give me some feedback. I always welcome feedback. Let's download the results. And let's be sure that I save that also in my drive. That's also good to do. Okay, that having done, show the feedback. Yeah, okie-doke, thank you. So that finishes our Kahoot quiz for now. You can leave the site, yeah. And then we come back, to the topic of today. closed loop systems and coordinate projection method. Last time we used a method where we used independent generalized coordinates, and there were two ways to do that. That was with Lagrange equations, and then we went up to the level of energy and went down to the equation of motion. And the other method was the TMT method, which just stayed on the level of force equals mass times acceleration. But the backbone of this whole thing, or the core of this method, is that you have to express the coordinates in terms of your generalized coordinates. So finding these expressions, finding xi is this ti of qj, is usually not so easy. And why is it not so easy? Well, if you have closed loop systems. And what do I mean with closed loop systems? Well, let me show an example of a closed loop system. So let's take this 4-bar mechanism, right? So we have 3 bars. This is the third one, and the fourth is of course the ground. So here we have a hinge, here we have a hinge. We have 1, 2, 3, and the ground is 4 bars. And then, well, to find out, Heike, we have to put a coordinate system, sorry, x and y, and we have a orientation positive. Then we have a number of bodies. So this is the first rigid body, this is the second rigid body, and this is the third. And then of course we have a number of dimensions for the thing. Yeah, let's put them in. So I had this distance called A, the length of this link is called B, the length of this link is called C, and of course the distance from the base or the fourth link is called D. Now if we count the number of degrees of freedom, then how does that go? Well, we first have to count the number of rigid bodies times 3, so 3 times, and we have 1, 2, 3 rigid bodies, minus the number of constraints. Well, we have 1, 2, 3, 4 joints who take away 2 degrees of freedom, because it's the x and the y connected. So, and the answer is 1. So we have 1 degree of freedom. So for this case, we have to choose some generalized coordinate, and I mean it would be sort of sensible to say, oh, let's take this alpha as a generalized coordinate. So meaning our qj in our case is then this single angle alpha. And what are our xi's? Well, our xi's are all the center of mass coordinates of all these 3 bodies. So x1, y1, phi1, x2, y2, phi2, and x3, y3, phi3. And our goal is now, of course, for this closed loop system to find the expression of these coordinates in terms of this one generalized coordinates. And that should be possible, because this is, it has 1 degree of freedom, so this is the describing coordinate. So with our xi is ti of qj, that's now the thing we're going to determine. So let's start. So we start with x1 equals, well, looking at the picture, and let's assume that the center of mass is in the middle of all the bodies, then we can say, oh, that's a over 2, right, times the cosine of alpha. And alpha is our generalized coordinate, this guy. Then y1 is a over 2 sine alpha. And, well, it's actually not so hard, right? And phi1 is, well, alpha, the angle in itself. Okay, then x2 is, well, then we move to this point, so that's a times cosine alpha, plus, and then b over 2, times, this angle, but it must be expressed in alpha. Yeah, so now we have some geometry problems. So so we have to draw this triangle, right? Or set of triangles actually, like this. And then we have given, of course, that here we have the angle alpha, and we have all these distances, A, B, C, and D. And now we want to know, of course, what this angle beta is in terms of the angle alpha, because we want to know we only have 1 degree of freedom. And that's like a geometry problem, right? So if you had like a compass, so this is a compass, so and a ruler, a ruler somewhere, and a ruler to measure distances, then yeah, you could sort of construct that. So the first thing you do is in this you divide it in 2 triangles, and then with the cosine and the sine rule you determine what all these lengths are, and then finally you can discover what the angle is, and then you have to subtract the minus angle of alpha, and it's sort of a tricky geometry problem, right? So it's not so easy. It's actually it's very complex, and I challenge you to write that out. And then we're done with beta, and then of course we also have to know this angle gamma, or in this case minus gamma, to finally come to this point, or this orientation of the bar, or whatever. So yeah, that's a difficult problem. Of course it's an old problem, so it was already solved, and there's a paper from Talbot from 1941 who already describes this. So let's look at that paper. So we're going to look at Talbot 1941, and I will put it also on Brightspace. Where is Talbot? Here you are. Yeah, and then we go to this screen. Yeah, and then I'll make sure that you see it. Oh, you can see everything. Oh. I rather like to use my mouse. So let me see. Yeah, that looks good, right? And this is the beginning of the paper. Okay, so this is the paper by Guy J. Talbot from the Research Division of the United Shoe Machinery Corporation. Now, why would a guy like Guy Talbot look from a shoe machinery corporation look into a 4-bar mechanism? And the answer is really straightforward. In those days, in the 1940s, all machines were mechanically. You had to find some transfer function for a pure rotary motion to a linear motion, or an up and down motion. And how do you do that? Well, by a 4-bar mechanism. Because there's like a nonlinear relationship between the input angle and the output angle if you have various sizes of bars. So therefore the Shoe Machinery Corporation was interested in this. And then how does he solve that? Well, how does he solve that? He draws the triangle just like we did, right? And then he comes up with a number of intermediate variables, like A is A sine theta, and then he continues, and then finally, after a lot of arc tangent and arc cosine, he comes to the conclusion what the output angle phi as a function of the input angle theta is, and that's this expression. And then, well, actually it's this expression, right, with arc tangent and arc cosine. And then he wants to know the speed relationship, so that's like the transmission ratio between the two. And then he wants to know what the accelerations are, and of course we see again this expression for the first order here, for the first order in the accelerations, that's the same coefficient. And then of course we see all these convective terms, which are quadratic in these input speed for the acceleration output. Now, to be honest, already for this very simple 4-bar mechanism, this is rather complex, and and even finding then these explicit expressions makes it a very complex task. And you can imagine if we then go to our transfer function here and we write all these arc cosine and arc r sine, it's becoming a mess, almost like this mess here. So that's not the path we want to follow. There should be another route to do that. So let's go to my notes. No, my notes here. Yeah. So Talbot-Baudet, and the conclusion of Talbot-Baudet, it's it's rather complex too, right? Rather complex too, even for such a small problem, for such a simple closed loop system. Yeah. Okay. So what is then the solution for that problem? So that's not an L. Solution. Well, everybody knows that the most powerful instrument of the engineer, most powerful instrument of the engineer, of the mechanical engineer is, of course, your scissors, right? So what are we going to do with the scissors? So we do like Napoleon, right? We do divide and conquer. So we do divide and conquer. The Napoleon approach. So having this 4-bar mechanism, so we have here these 4 bars connected in the hinges here. What are we going to do is we're going to use our scissors to cut the system. So we're going to cut the system, like for instance here. If we cut it here, then we suddenly have an open loop system. So we make cuts such that we get an open loop system. That is our solution. But of course, if we make cuts, we also have to add, plus we have to glue it with constraints, right? But we can do that. We did that in the past, so we know how to use glue, add the constraints. So if we do that, then let's draw the figure again. So we had this first bar, then the second bar, and then the third bar. And on purpose now, I cut it open, right? Like there's an opening here now. So this was originally the part, and I should put the opening a little bit more clear. So I'll take this, put it like here. Yeah. So there's clearly an opening there. Put the coordinate system in, right? So coordinate system X and Y. Show what the orientation is, and this was body 1, this was body 2, and this was body 3. The lengths were A, B, and C, and this distance was D, right? Okay. And then we have to put in, since we made 2 cuts, we also have to introduce now 2 coordinates, which is rather obvious here. So initially we had our generalized coordinate alpha. Now we add a second generalized coordinate, here the angle beta, and a third generalized coordinate gamma. And I write on purpose minus gamma because it's flipped down and not up. So now our QJs of the problem are larger, and we have alpha, beta, and gamma. Now we have more generalized coordinates, and of course we have to also add 2 constraints. I will come to that in a second. But first, with these more generalized coordinates, we can now write easily down what is xi ti of qj. So that becomes again x1 is a over 2 cosine alpha, right? And y1 is a over 2 sine alpha. And phi 1 is then alpha. But now x2 is a cosine alpha plus b over 2 cosine beta. y2 is a sine alpha plus b over 2 sine beta. And phi 2 is, well, in this case, just beta. And like, oh, don't rotate the paper. Then x3 is, well, we start with x2, of course, a cosine alpha, well, not x2, but the extension, of course, plus b cosine beta plus c over 2 cosine gamma. And for the y, the same, but then the sines. B sine beta plus c over 2 sine gamma, and then phi 3 is gamma. Now, having put those all in order, it was very easy to write down this mapping, right? And now we just have to add the constraints, and the constraints are two constraints, and being that we have to close this gap. So you could say, if you call this point D, then the delta at xd should be 0, or in other words, we calculate what the position is, and then we compare it to that position. So we say a cosine alpha plus b cosine beta plus c cosine gamma minus, and then this distance was d, right? Minus d is 0. And the delta y at d is 0. Becomes then everything with a sine alpha plus b sine beta plus c sine gamma, and the distance here is 0, so it should be 0. Now, writing down the equations of motion for this constraint problem, for this, we learned with the TMT method, and then the only thing we now have to add are these constraints. So the equations of motion, equations of motion, then take on the following form. You could say, well, we have this generalized mass matrix, which I explain in a minute. Then, of course, these are my C of Q is 0, right? And maybe I put a K. Did I use a K in the past? C, K, or QJ. So here I then have my constraints differentiated with respect to a generalized coordinates, the Jacobian of that. And then my coordinates are my generalized coordinates. And then I have two Lagrangian multipliers in this case, because I have two constraints, equals, and then on the right hand side I have my generalized forces Q. I will come back in a minute what they are. And then of course we have the constraint equation, these, but then differentiated twice. So CQ, Jacobian times this acceleration, here we have all zeros. And then here we have minus C, Q, Q, Q dot, those convective terms. And now to complete, of course, what is this M bar? This M bar is, of course, now I have to check my notes because I always make errors there, is of course this transformed global mass matrix with the Jacobian of this transformation function. So it's Ti, L, M, I, J, Tj, K. And then on the right hand side, this vector is of course Q bar are my forces. So the outcome is an L here, TL, minus Ti, L times, and then the transformation of the forces at the center of mass, minus Mij, and these of course are the convective accelerations. Need I write them down? No, you know that. Just look it up in the TMT part. Okay, so divide and conquer. We cut the system, we open it up, we have more generalized coordinates, so we add two constraints, then we formulate our equation of motion, and then from the equation of motion we can solve for Q, Q double dot in a position and lambda in a position. Now given those, then in the next time increment, and meaning you use some numerical integration scheme, and it doesn't matter what. Let's say we do a very simple numerical integration here for now. Then we say, oh yeah, the new position is the old position plus h times the velocity, which is the state, and the new speed is the old speed plus h times the acceleration. So that's a pretty straightforward thing. I use an Euler step here, but it doesn't matter which type of method you use. You have some numerical integration scheme. By the way, notice that we don't use the Lagrange multipliers. We get them for free. They are like the constraint forces in the joint. And for the numerical integration of the ODE, we do nothing with these. But note that these are estimates. That these are what we call estimates. Yeah? And in general, they will not fulfill the constraint. Will not fulfill the constraints. I mean, where did we put in that if we add this up, that the result is on the constraint? I mean, we use the constraint to find accelerations, which are on that constraint surface, but if we then predict from these and from our state what our new position and speed is, they need not necessarily be on the constraint surface. Or in other words, if you now calculate C k of this x, with strange notation, that the one is now meaning the new position, then you will see that in general that's not zero. It should be zero, of course, it should be zero. So now we are in trouble, and you can imagine that that if they do not fulfill the constraint, and then you move on to the next time step and to the next time step, then you are slowly building up an error. And to be honest, you already saw that in the one of the first lectures, I think. And let me see if I can, by magic, get that back again. Where is my mouse? Yeah, okay. So was it in lecture 1? Was it in lecture 2? Yeah, it was in lecture 2. And now I have to open this up with Google. Does that work? Yeah, this so this was the simulation of this double pendulum falling, and remember what happened? We got this gap, right? We get these gaps. So let me run it again, and then it started very nicely, but it opens up, and that's exactly the problem we will get when we just continue with this scheme. We will slowly build up errors, and by not fulfilling the constraints on these estimated values, and then we slowly will drift off, as you have seen in this double pendulum falling down. So we have to find a way to get these coordinates back on the constraint surface. So you could say, and there's a nice picture to draw for that, that these values are actually estimates. So let's repeat that. So I'm gonna copy this, yeah. duplicate it, and then where are you? Yeah, put it here. So these are what I say, oops, these are the estimates. Estimators. And to show that, I put like this slur on top of it. And again, then we see that this CK of this slurred value is probably not 0. Or in other words, there goes a nice picture with that. You could say that the constraint is like what we say is like a constraint surface. Like we people are constrained to live on Earth if you cannot fly. So our constraint surface is a sphere. So in general, we then draw this constraint surface as some curved space thing. Okay. Now we start from this point here, which is very nicely on the constraint surface. So this is CK of Qj. Yeah? So it's a multi-dimensional thing. Is 0. So Q0 is perfectly. This vector is perfectly on the surface. Then we do an estimate, and let's say our estimate is somewhere here. So this is our estimate Q1, and it's clearly not on the constraint surface. So if we calculate this, then it's equal to 0. Or in other words, it's a little bit above the surface. Now, how do we get back to the surface? So you can go like this, or you can go like this, or you can go like this, or I mean there are like multiple ways to get back to the surface. Get back to the constraint surface. And the question is, how are we going to do that? Here, point, this point, this point, this point. There should be all close in the neighborhood of our estimate, of course. Looking at the clock, I think it's now a nice way to think about this and take a break. So we do a coffee break. And we will return in 15 minutes, right? Okay, stop the recording. Stop.